cases. So to cover the first case, we've got temperature and humidity data, and there's a couple of other bits of data as well, like battery and relative signal strength, which tells us about the wireless unit that's identified by this unique MAC code. And then paired here where we say glow sensor temperature humidity 1, and there's up to 3 sensors that can be brought in. So this is the type of data that is flowing over the network, let's say, so the DCC network. This is what we would want to get as an end result from that network. And we can see that we wouldn't be able to send this JSON packet, so this quite well-formed, easy-to-read packet, we would not be able to send that through the DCC network because it can only handle binary data. So if we look at an encoding scheme for this JSON that's compact and is binary, we've chosen what it says on the 10 here, so it's a compact binary object representation, or CBOR. And CBOR is a well understood protocol for carrying JSON-like data through binary, and it has features like compression and white space stripping, so that it doesn't get, doesn't chew up a lot of bandwidth for what is just sort of basic formatting data. So if we look at the encoding so that we can create some test data, for instance, we wouldn't normally need to do this, but in this case we want to be able to test that our system's working. We copy this JSON and we stick it into a postman call, which I'm going to make this smaller so we can actually see. So this body data, I've just pasted it into a JSON body that I'm going to send to my local machine, and I should get back an encoded CBOR file, excuse me, which you can see here. So the CBOR is what we would expect to receive from the DCC alert that's coming to us. And this is what the supplier or utility would be receiving as a billing data log data packet. So now we have some test data. Obviously that's handy, but the real data that's coming through, we want to be able to decode that data. And so when we get a packet back from the system, we will then go to a decoding endpoint and be able to decode that, and as you can see, the values come back. So this is just basically a round trip of our encoding and decoding so that you can see that the encoder and decoder is working. And this is deployed as a web service, so it's actually available. It's running on my local machine, but it's available as a web service that can be called by Utilita to be able to decode this data that's coming through. Furthermore, there's and the documentation here sort of shows these basic concepts, and then this is where the JSON that comes out would result in pipelining that into the application. So this is an application which could be to syndicate this data out to other applications like HTC calculations or a database so that it's saved, and then analysis can be done later on temperature and humidity data. The timestamp that's set is coming from the sensor itself, so this should be consistent with the time in which the data was collected. The next area is actually shifting gears slightly, and this is about decoding the schedule information. So these are DLMS messages, or DLMS custom messages, which are represented in a complex structure and they represent calendars and schedules for the proportional control. In the documentation, we put a bit of background around how these can be used, so things like seasons and different week profiles, day profiles, special days. It just gives a flavor for what can be encoded in terms of rules, and a little sort of like kind of, I guess, easy to digest example of like start end times and how you might represent, in this case it's a tariff, but the structure's the same for control schedules as well. So let's get into the proportional control. So the proportional control DLMS message is sent from the supplier, or from utility in this case, to the head-end system. So the head-end system is DCC, or the adapter, let's call it more precisely, is the DCC adapter that's owned and operated by Utilita. So this message would be encoded using encryption keys and other identifiers that would be Utilita's identifiers. And what I'm representing here is actually a message that's gone through decryption and would be something that would be on the device and readable to the SAPC device itself. So the SAPC device has a decoding function which could be used, let's say, to interpret this message into a schedule. And so let's just give you an example, and we'll come back around to context again so that you can remember where this is flowing from. So again, it is represented with first a well, let's actually look at the full decoded message, because that's probably easier to get your head around. And the full decoded message in this case, so I've posted, again, there's a service which we're hosting, which will take a full message, and you can see it looks similar to the one I showed you before in the documentation. And then by posting it, we get a set of JSON, or easier to read, more human readable information. So the first section that we get is a MAC header, and this is a test message with a test MAC address, and therefore it's not got necessarily a reality in it. The message length is dictated by the amount of items in there, but you can see the header is there to kind of identify and it doesn't actually encapsulate the whole message. It's just there, so you can see the MAC header is just one item in the JSON structure. And then the grouping header has more information about things like the originator system, so where that's coming from. So this would be the supplier's originating identifier, or EUI. They'll have item counts, so they'll know how they can check that the message was actually delivered, and the counter will go up, indicating that a new message has been sent. This is the EUI of the SAPC device itself, so this is the recipient of the message. There's some date time stuff in here, which I'm sort of ignoring, but and again, there's various kind of control information, let's say, about the message, which we don't need to talk too much about, but it represents that this is a class of DLMS custom message, and it should be interpreted in a particular way. And that particular class is an access request, and the access request is that identified by that the kind of information that's encoded in here. So the 20 indicates that it's a DLMS message. So we'll go back to my documentation here, and this is kind of explained. So, you know, this is indicating that this is an access request, so that D920 that I just talked about. And that's going to have a further kind of like, I guess, guiding information about what you would find inside this access requests. So this is like a plural access requests. And then we can see that there's going to be 4 items, and those 4 items are going to be made up of, firstly, a special days entry. So these are all of the special days. So this might be Christmas Day, maybe Easter, maybe holiday day, and you may want your schedule to run differently on those special days. The second is really the main interest. So these are the calendar entries. So these are the, how do I want, on a given day, like how do I want to run my control schedule. And then there's some next date time stuff, which just basically says, okay, what's coming up? What's my schedule look like that's coming up? I kind of won't go into too much details on these because they're actually changing quite a lot, and we wouldn't probably use them because we're going to be forwarding this to a more intelligent device that will be interpreting the calendar requests and any kind of special day provisions that need to be in there. So the example message that I'm going to show, again, is quite complex. You can see all the string information there. But if we look back to the decoded message, we can see that there are 3 special days that are specified. So we have Christmas Day, we have the 1st of May, and we have the 10th of June. And these are occurring every year. So they're not December 2025 necessarily, it's the 25th of December for every year. Same with May 1st and the 10th of June. And that's up to whatever schedule you want to set, whatever special days you want to sort of designate. So if we go back down into this decoded message, we can see, you know, again, this is telling us what the access requests, so these plural of access requests that we've got 4 of them, so we have 4 sections to deal with. So the first one is the special days table that I talked about before. The next one is the schedule information. Sometimes schedule and calendar gets a little confusing because some people refer to it as calendar, some people refer to it as schedule. I think technically it's schedule in documentation, etc. And then we can see that this is going to be made up of calendar entries, which are, so the schedule is made up of calendar entries, which are of this sort of type. So this type is an auxiliary controller calendar, and it carries this OBIS code that is special and has a reference on how to interpret it. So close that one down. And then we talked about these other 2, which again were sort of the passive, active GBCS set. So I'm going to close those down. So let's get into the special days, because I was trying to make a kind of point that it's the 25th of December every year, and that's designated by the 0C, and hex is 12, so that's December, and then 19 is the 25th. This means every, so this F in the front means every year. If we put a specific, you know, like value of 2025 in these 2 to accommodate larger than you know, it wouldn't be just 1 byte, it would be 2 bytes to express 2025, then it wouldn't be every year, it would be a specific year. But given that we're going to do that every year, then we've got FF. These items tell us how to interpret the date. So if we wanted to have a specific date time, I guess you could be allowed to do that potentially on a special day, but I don't think that's the intention of it. So the 0905 means it's an octet stream. 05 means it's of a certain date type. If we look again at May 1st, it's encoded in the bit stream as well that I was showing. And then that's the end of the index, so it tells us how we're going to be able to refer to it in the next section. So this is special day 2, whereas that was special day 1. So in the notes being 2 is special day index 2, and then we've got the 10th of June every year is special index 3. Okay, so that being special days, a little bit complicated. Like I said, the meat of what we're looking at is around is actually around the 12 items which make up the actual schedule. And again, there are calendar entries in the schedule. If I flip back over here, we're explaining like how did this get encoded, how is it described. It's a good read in here, but this table is a really handy thing to kind of look at. And it shows that, okay, each entry is going to have a unique index. It's going to say whether it's enabled or disabled. There's an action script, which in our case is going to be an OBIS code, so it tells us how to interpret some of the information that's contained within this entry. We have a switch time, which is kind of obvious, so it means start the schedule item or the calendar at this particular time. This is more on a reset or a power reset, so it will say something like, well, after a power reset, wait 15 minutes after power reset to execute the command. I've given all of mine validity windows of FF, which means start anytime. So it's unspecified, like you can start anytime after power outage. You can say for these items as well, so 6 a.m., you can say, well, what weekdays do I want this to be able to execute? So in this case, it's showing an example of Monday through Saturday. And then this is how we might observe our special days. So there's a slot for, so you can't have an infinite number of special days. I think it goes up to 9 by the specification. So this is table 23 from the DLMS Blue Book, and it describes how these schedules, can be encoded. And I've got a schedule slot, or sorry, special day slot 1, which would be index 1 in my case. 2, 3 is not shown. Again, this is just an example table, so it's not really indicative of what I have encoded in my message, but it shows you what's possible. And then there's a date range, so this will say, okay, what dates can I observe this from? So that allows you to set a kind of effective begin, end of these schedule entries. So we're going to start decoding this beast of a table in DLMS, and the decoding is fairly easy once you get your head around it, but it's something you've got to really be paying attention to and to be able to understand it. In this example message, so I think the full message is somewhere up here, so that's the full message. I've cut out the headers and I'm fast forwarding to where this kind of table starts to get represented, and it's in this bit stream here. And it's indicating that we've got 10 elements which will conform to a particular structure, which the structure is this table, if you start to refer to it. and then I'm taking a specific item out of this and I'm starting to decode it. So I show, the action script which will be used. So this is defined in the GBCS standard in section 7.36, and it's not, it deviates from the DLMS standard. So that's indicating that you're going to have to interpret this a little bit differently than what that table would absolutely show you. And the main difference is in this area here where we're looking at how do we indicate which auxiliary load controller we're going to actually control, and where is that proportion, so how much from 0 to 100% will be switched on or activated. And that's where this complex interpretation comes in. It's only 3 bytes, but it's the 3 most important bytes probably in the table, or some of the 3 most important bytes, and that's encoded in. So if you look here, it's about interpreting the XXX, I guess, represents the OBIS code or the action script that we're going to run, and then just following that, there's a little data before we get to the switch time. It's almost like there's another column here in some respects for this. So you can see here's my OBIS code, which is my action script, some kind of I guess detailed specific information from GBCS, and then that switch time starts to kick in, and then we got validity window, and then we can see weekdays, special days, etc. And that kind of like takes you, and then there's a begin end, which I haven't actually decoded, but we'll get into that in a second. So switch days, or the days that you should observe. It's a complex binary encoding, so it's represented by 7 bits, and there's a leading bit which is always set to 1, which says to take so he's taking it's taking 7 bits according to this, and then you set the high bit to 1, and the next ones represent positions of the days. So the 7 is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So you can see this is running Monday, Tuesday, Wednesday, Thursday. Monday, Tuesday, Wednesday, Thursday. And yeah, not Friday. I don't know why they've got Friday in there, but it's Monday, Tuesday, Wednesday. And then special days shows that we're going to observe the first 3 entries in our special days. So this is like our overriding 3 special days will get triggered based on that we will observe them. You could ignore them if you said 000, then it would ignore the special days for the time slot. Okay, so let's go back to our decoding example. And again, this gets a little hard to follow. Hopefully you don't need to take a break, but do a brain stretch for a second, and we're going to start to dig into how this relates to like a real schedule that you might be able to see. Okay, so in the first item, which is equivalent to the kind of first row in the table that I showed you before, table 23, sorry, it's down here is so it says we have 12, we're going to have 12 items, so 12 rows. And you can start to see some of these things like the index and the enable being true. This is telling us how to interpret so this is the action script that we talked about. And then this is that special data, so that funny like special SAPC proportional control data. And it's interpreted by these 2 bytes. The 12 just indicates that it demarcates the type of interpretation that you want to give. So like 0906 says, okay, this is an octet stream 09, and 06 means it's the next 6 bytes. 1, 2, 3, 4, 5, 6. And then if we were to map those 6 bytes, so you can see where the zeros line up, and then where the 10, which is A, lines up, 103, which is 67, lines up, and then 255, where the FF lines up. So you can see it's kind of, once you get your head around it, it's not too bad. This one's a little wacky, though, because it's so special for SAPC. And what it's saying is that in the documentation, if you read carefully, it's 2, it's meaning I'm going to, I'm telling something to set, so I'm saying output, or send not input or take from the grid, but give to the grid, or not give to the grid. I shouldn't say that, because that's more like energy flows. But it's basically, I want to say, this is an output schedule. So I'm going to interpret this as run it. Say that I'm on and I'm going to be consuming energy with a 2. The next byte, or next part of the byte, or nibble of the byte, maybe not even, I guess it's a nibble or word, is a 1. That indicates device 1, and you can have up to 5 devices. So we're gonna have 1, 2, 3, 4, 5, and a SAPC, and you should never see that number go beyond that. And then the D0 is telling me 80%, and the 80% is encoded in a really quite funny way. So because it has a 0 to 100, you don't need that much space. They've decided to encode it with to fill up the byte. There's basically a leading 1 on the bit. So let's have a closer look at that, just to be thorough in our coverage of this. So if I was looking at this from 80%, let's say decimal to binary, I'm going to encode 80%. So I'm looking at this, and there's only 7 digits required. So it's only 7. It's even to 100%, it's only ever going to be 7 digits. That's all that's required. So in order to give it a full byte size, they basically pad the first. They could have chosen any pad, but they chose 1 as the front padding for how to encode this. So if I want to say 80%, convert that to binary, I'm going to copy this, and then I'm going to flip back and say, okay, let's go from binary to hexadecimal so we can see how this is represented. I'm going to put a leading 1, padding in, convert it, and 80% looks like D0. Again, flip back to our D0, yeah, that's 80%. Great, all ties up. So again, first byte in this structure represents the direction, output, input. 1 is input, 2 is output, and then the next digit represents the device number. So this is just enumerated. So this is device number 1, and then I've got 80% encoded by this D0. And then you can see the next item is going to be when. So when is my start? When do I execute this? When do I start it? What time? And this is represented by, again, octet stream 04 tells me how to interpret this as a time, and it's hours, minutes, seconds, hundredths of a second. And it's readable because 1 is 1 in hexadecimal, 0, 0 in hexadecimal, so this is quite a readable example. I can see it's 1 a.m. It works on a 24-hour clock. Yeah, no big deal. Oops, sorry for the scroll glitch there. Let's go back up. I've scrolled down too far by some mistake. And then this is our window. So this is saying you can restart at any time. So if a power outage, go ahead and execute the schedule at any time. This is our days. So remember we said it's a bit, it's interesting. It uses the 7, so this is bit stream. 04 means bit stream. 07 means take the 7 bits. And then this is the actual value that you want to strip the 7 bits from. So you can see that's 7 ones. So this means every day of the week. So Monday through Sunday. Our next bit stream is representing the special days. And I talked before a little bit about that. So this is a again, a bit stream, 3 bits, and we're taking the first 3 bits to represent the special days, because you remember that that table has like a slot for the special days, so it's kind of left aligned, let's say. So S1 is the furthest left, so that's why we're taking the first 3 bits, and we don't pad it out with zeros. It's just interpreted as have it or not. And then we've got a date representation, which is our effective start and our effective end. Here I've got this encoded, so 09 is octet. This tells me it's a date. 7 is the month, so that's June. I think I get this right. No, sorry, bad. This is the year. 07 E9 is 2025, and then 06 is June. 11 is 17 in hexadecimal, and then this is about a kind of like something indicating like every hour of the day, so it's like all day. Again, you can sort of see, you know, not to drone on about this too much, but it's, once you mastered it, it's kind of fun to be able to decode it. So C is equal to 12 in hexadecimal, so that's December. The 07 E9 is familiar for 2025, and then 17 is equal to 23 in hex. So you can see how these schedules sort of run out. We didn't cover the device indicator, but yeah, we did cover the device indicator. Sorry about that. And then this is the index, so index of 1. So now when we come down to index of 2, this is the next entry. And you can again see output 1 at 80%. It's execute 7:30 a.m. It's got a different run pattern, so it's only 3 days a week. So that's Tuesday, Wednesday, Thursday, observing all special days. All good. We can go to the next item. So we're saying, okay, output at 100% at 9 a.m. And then we've got, again, Tuesday, Wednesday, Thursday. And all special days are observed. And we've got a start and end range, which is good. So on and so forth. This kind of shows the encoding for this device 1 and how these get interpreted. And we put a couple of challenging ones in. I'll scroll down to a couple of challenge ones. Like, actually 64 is not that challenging, but you know, there's a couple of cool ones like 29%. So that's encoded as 9D for output 1 at 5:30 in the morning for the time schedule we talked about. Then I'm gonna kind of drop down here towards the end, and we can see a change in one of the items, which is saying, okay, now I'm going to talk about device 2. So I've got output, device 2, 80%. Starting at midnight, all days, observe all special days. Okay, so that's the decoding part of it. And this is where we will pick this message up from the SAPC device, from the Modbus registers, which are on the SAPC device. They will basically be this number of registers that we will pick up and shove into this decoder, and we get all this structure, and then we're able to use that structure in other places. So if you think about that, you know, number of characters and stuff, we're going to be hitting quite a few registers in the 30,000 range to be able to read, bulk read. So 2 of these digits equals 1 register. So if I copy that and put that into like a, let's say something that will count the characters. That character count should have told me what it is, but maybe I need to make the window bigger. There we go. So I'm going to have 814 bytes of information, or 814 registers. So that's going to take me from register 30,000, roughly. I think we might start a little later than that because there's some control information, to 30,814. I'm going to read all those registers out, and then I'm going to have this nice binary object once I've read those registers through a Modbus read, which is any device can do a Modbus read. And that's why we have this decoder. It's not because we could decode this ourselves, and we could say, oh, we're just going to decode it ourselves. But the point is, we want to preserve the kind of DLMS specification just in case anything changes in the future. We don't want to rewrite the SAPC device, and we figure that if somebody's got a generalized Modbus reader, they're not going to be able to make any sense out of this. So we need this kind of decoding thing as a service that people can shove up and decode. Okay, why do they want to decode it? Why don't they just take action on it? Well, because probably they're going to have to interpret this into something else. And we've showed an example, and this is where I'm drawing the links back to Home Assistant, is we've shown an example where we're taking this exact schedule, and I went through a few of these, and you should be able to see these match. And we'll kind of check one of these just so you can see that we've actually taken this message through a process, and that will match with sorry, just was looking at CubeSats, so you will have to forgive my curiosity on CubeSats, and then let's find the Home Assistant instance, which I thought I had here, but I am not finding it at the moment. So what I'm going to do is splice in the video of, oh, here we go, here's Home Assistant, and I'm offline from the Home Assistant, so I'm going to splice in the video, but and then I'll show you. I might get lucky now. I'm offline. Joys of recording in a sound booth. No Wi-Fi signal in here. So the EV charge point represents for us, in our examples that we showed you before, it represents the device 1, and the heat pump represents device 2, which is really great, and it tracks with our example that we were showing before. And I will try to splice in the video and put some commentary on that next. But thanks for listening. It's rather long.